Hey class, in today's lesson we're going to talk about vectors in the plane, which is found in section 6.3 part 1. Our objectives are to represent the vectors as directed line segments and to write the component form of vectors. So for some vocabulary, it says many quantities in geometry and physics such as area, time, and temperature can be represented by a single real number. Other quantities such as force and velocity involve both magnitude and direction and cannot be completely characterized by a single real number. So if you look at the figure, you see a line segment. The initial point is P, the terminal point is Q, and it represents a segment PQ. So it says to represent such a quantity, you can use a directed line segment. The directed line segment PQ has initial point P and terminal point Q. Its magnitude or length is denoted by, and then you see that notation. So you'll use, for magnitude, you'll use kind of like the double stacked lines. And again, I hope you can see, and it's kind of dark on the screen, but there is an arrow right there that lets you know which direction that the segment is going. A little bit more vocabulary. So it says two directed line segments that have the same magnitude and direction are equivalent. The set of all directed line segments that are equivalent to a given directed line segment PQ is a vector V in the plane, written V, or that vector, equal to PQ, or segment PQ. Vectors are denoted by lowercase bold letters, so you'll start seeing more lowercase bold letters, and again, those are vectors. All right, so in example 1, it says let U, or vector U, be represented by the directed line segments from P of 0, 0 to Q of 3, 2. And let V be represented by the directed line segment from R, which is 1, 2, to S, which is 4, 4. Show that they are equal. So if we use the magnitude, and to be honest, the magnitude formula has not been given to you yet. Essentially, what you have is the magnitude of some segment would be the square root of x1, or x2 minus x1 squared plus y2 minus y1 squared. Okay, so for us, for the magnitude of PQ, of the segment PQ, we would get the square root of 3 minus 0 squared plus 2 minus 0 squared, and that would give you the square root of 13. Okay, same thing for the segment RS. We would use the square root of 4 minus 1 squared plus 4 minus 2 squared, and that would still give you the square root of 13. So they have the same magnitude, and then as far as the slope goes, or the direction goes, they have the same slope. So if I look at my graph on the first one, for PQ, I would go up 2 and to the right 3. So that slope is 2/3. And then for the other graph, the RS segment, I would go up 2 and again over 3. So it's still 2/3. So not only do they have the same magnitude, but they also have the same direction. Therefore, vector U does equal vector V. All right, so component form of a vector. So the directed line segment whose initial point is the origin is often the most convenient representative of a set of equivalent directed line segments. This representative of the vector V is in standard position. So in other words, we really like for things to be in standard position because it comes from the origin, and the origin automatically has 0, 0 attached to it. So it makes it easier mathematically. So a vector whose initial point is at the origin 0, 0 can be uniquely represented by the coordinates of its terminal point v1, v2. This is the component form of vector v written as vector v equal to v sub 1, v sub 2. The coordinates v sub 1 and v sub 2 are the components of vector v. If both the initial point and the terminal point lie at the origin, then vector v is the 0 factor and is denoted by vector 0 equal to 0, 0. So the component form of a vector's definition and formula is that the component form of a vector with initial point P given as P1, P2, and the terminal point Q given as Q1, Q2 is the directed line segment PQ, Q1 minus P1, comma, Q2 minus P2, which would give you V1, V2, which is a vector. The magnitude or the length of the vector, which is kind of what I gave you before, and you see it Q1 minus P1 squared plus Q2 minus P2 squared is essentially V1 squared plus V2 squared. It's the square root of it. So if vector v equals 1, then vector v is a unit vector. And moreover, if vector v equals 0, if and only if vector v is a 0 factor 0. So let's kind of apply this and see. So from example 1, the vector u that we had where the point was 0, 0 and q was 3, 2 is actually vector u given as the directed line segment PQ, and those were 3 minus 0 and 2 minus 0, therefore the vector was 3, 2. And the vector v from the point R, 1, 2 and S as 4, 4 would give you vector v from the line segment or the directed line segment RS, which would be 4 minus 1, comma 4 minus 2, which is still 3, 2. So now with using vectors, now we can truly see that u does equal v. And again, vectors have, not only do they have the same length, but they have the same direction. So finally, it asks for us to find the component form and length of the vector v that has an initial point 4, -7 and a terminal point -1, 5. So vector v, and I'm trying to make this look bold, so that's a vector v equals, understand that, let's go ahead and label this. Let's make this P1, Q1 and make this P2, Q2. So in vector form, that would be -1 minus 4, comma, 5 minus a -7. That would then give you -5, 12 as the vector. Okay, then from there, where it asks for us to find the length, remember length is the magnitude. So the magnitude for us would be the magnitude of our vector, which is equal to the square root of each of those squares. So that'd be the square root of -5 squared plus 12 squared. -5 squared is 25. 12 squared is 144. Add them together, you get the square root of 169, which is going to be 13. So our length is 13. And also kind of just going back to the rules about square roots. Remember, technically, if you take the square root, you would get a positive and a negative solution. However, we would not take the negative solution simply because the negative version, you can't have negative length. So that is it. If you guys have any questions, please be sure to come see me for tutoring.